Welcome to HFCL Time Machine. Past, present, future, all connected.
Let's step into today's chapter, where we explore high-density fiber solutions and what it means for the future of sustaining the massive data demands of the AI era. I am your host, Sophie, and we're heading into a deep dive on future trends in optical fiber technology. Our goal is simple: capture crisp, high-quality knowledge from our internal experts that the world can understand and appreciate. Today, we have with us Jayuti Prakash Das, who is leading new product development in optical fiber cable products at HFCL. Jayuti comes with extensive experience in fiber design, manufacturing, and deployment. Thank you for joining us. Let's get started. Before we dive into trends, can you briefly explain how the optical fiber ecosystem is evolving today?
Globally, the shift is toward ultra-high capacity fiber networks, low latency connectivity, and sustainability-focused designs. We're seeing demand for denser fibers, smarter cables, and radically improved installation efficiency. The ecosystem is moving from just fiber to fiber, intelligence, and flexibility. If you look at how fiber networks are being built today, the conversation has clearly moved beyond just speed. Yes, higher capacity and lower latency are still essential, but what's really reshaping the ecosystem is the need to deploy networks faster and smarter. Operators are no longer building in greenfield environments. They're working around crowded ducts, tight bends, urban constraints, and ambitious rollout timelines. That's why we're seeing growing demand for denser fibers, more flexible cable designs, and solutions that can be installed quickly, often using existing infrastructure with minimal disruption. For example, our intermittently bonded ribbon, or IBR cables, are offering high fiber counts in compact diameters while maintaining flexibility and installation ease, perfect for hyperscale data centers, urban deployments, and high-density FTTX networks. Our IBR designs have been recognized globally, winning accolades such as the Lightwave Innovation Reviews and the 2024 ISE Network Innovators Award. In many ways, the industry is shifting from how fast can the fiber carry data to how fast can we get the network live. It's this combination of capacity, flexibility, and deployment efficiency, reinforced by industry direction from bodies like the ITU and FTTH Council, that defines how the optical fiber ecosystem is evolving today.
That is a fascinating overview of how the landscape is shifting. Building on that momentum, what are the top 3 future-ready optical fiber technologies that will redefine networks in the next decade?
When people ask me what's going to fundamentally transform our networks over the next 10 years, I point to what's happening at the physical layer. We're hitting the boundaries of conventional fiber, and the industry is responding with 3 game-changing innovations. First is ultra-low loss and high-density fibers. HFCL's ECA ultra-low loss single-mode fiber tackles the key bottleneck in long-haul, metro, and FTTX networks. With loss as low as 0.19 decibels per kilometer at 1550 nanometers and strong macro band performance, it enables longer unrepeated spans, lower OPEX, and energy-efficient deployment, even in tight ducts. Paired with bend-insensitive, high-density microfibers, networks can now host thousands of fibers in compact diameters, addressing space constraints in data centers and metro networks. At HFCL, for example, we have already developed the 3456 fiber cable, and the next target is 6912 fibers in a single cable, delivering scalable, resilient, and future-ready networks without costly civil upgrades. Second is hollow core fiber. This is the paradigm shift. Light travels through air, not glass, 50% faster. We're talking 33% latency reduction and 1.54 microseconds faster per kilometer. For high-frequency trading, real-time AI, anything latency critical, this changes everything. Long-term, it replaces multimode fibers in data centers. At the same time, we'll continue to see ultra-low-loss solid core fibers, such as G654E class fibers, play a critical role in long-haul and high-capacity backbone networks. These fibers push attenuation limits lower and form the bridge between today's networks and tomorrow's hollow core deployments. And last but not least, multi-core fiber. This fiber multiplies network capacity without increasing cable diameter. In high-density deployments, operators can achieve 4 to 12x more fibers in the same diameter compared to traditional designs. This is ideal for data centers, FTTX densification, and 5G or 6G backhaul, where space is at a premium. While the technology delivers substantial capacity gains, short-term challenges like splicing and backward compatibility need careful planning. The question isn't whether these technologies will reshape networks. The question is, are you ready to deploy them?
Those are great insights. Additionally, why is hollow core fiber attracting so much attention worldwide?
Because it solves three things simultaneously: latency, nonlinearity, and power efficiency. With light traveling mostly in air, attenuation lowers, and networks can run faster with fewer amplifiers, ideal for AI data centers, algorithmic trading, and future 6G backhaul. This fiber offers 30% faster signal speed, lower optical loss over long distances, minimal nonlinear effects at high power, superior power handling without thermal damage, highly tunable dispersion control, reduced chromatic and polarization mode dispersion, better environmental resilience, mid-IR transmission capability, quantum and terahertz readiness.
Incredible. Moving to physical deployments, what are the biggest innovations coming in fiber cable designs?
Fiber cable innovation is increasingly defined by how efficiently networks can scale in constrained, regulation-heavy environments. And this is where HFCL has been deliberately focusing its design roadmap. HFCL's work in ultra-lightweight, high fiber count cable design addresses the realities of aerial and microduct deployments, where reducing cable mass while preserving mechanical integrity directly impacts span length, installation speed, and overall rollout economics. A key differentiator is HFCL's leadership in extreme density fiber designs, extending well beyond 1,728 fibers to 3,456 fibers and up to 6,912 fibers designs. These designs enable exponential capacity growth within existing ducts, conduits, and data center pathways, allowing operators to scale without civil rebuilds or space expansion. In data center and enterprise environments, HFCL has placed strong emphasis on high-density ISP cable solutions that are fully UL-listed and CPR compliant. Fire performance, smoke emission, and reaction to fire behavior are engineered into the cable structure from the outset, making these designs suitable for hyperscale, colocation, and mission-critical facilities where regulatory compliance and operational safety are non-negotiable. HFCL is also advancing low-friction jacket technologies to support longer installation lengths with lower pulling forces, an important advantage in dense data center raceways and long microduct routes where installation efficiency and fiber protection are critical. Sustainability is another embedded design principle. HFCL's next-generation cables incorporate eco-optimized materials that reduce plastic usage by up to 40 to 60%. Aligning large-scale fiber deployments with operator ESG and lifecycle carbon goals. Finally, HFCL is integrating intelligent sensing capabilities into selected cable platforms, enabling real-time monitoring for strain, temperature, and security, transforming passive fiber infrastructure into an actively managed network asset. Collectively, HFCL's approach positions its fiber cable portfolio, particularly its CPR and UL-compliant high-density data center cables and 6,912 fiber architectures, as infrastructure designed not just for higher bandwidth, but for safer, denser, faster, and more sustainable network scale-out.
It's great to see sustainability and safety baked directly into these ultra-high-density designs. To pull off these complex architectures, how will cable manufacturing evolve with automation and AI?
Cable manufacturing is moving from process-driven to intelligence-driven, and AI is becoming the control layer that ties quality, yield, energy, and speed together. At the production level, robotic fiber drawing combined with AI feedback loops is enabling micron-level control over diameter, concentricity, and coating thickness, far beyond what manual tuning can sustain. Instead of reacting to defects, AI-driven vision systems now detect surface flaws, coating inconsistencies, and micro defects in real time, triggering automated corrections or segregation before yield is impacted. The bigger shift is toward closed-loop optimization. Machine learning models continuously adjust furnace profiles, draw tension, and pulling speeds based on live data, maximizing throughput while maintaining optical performance. In parallel, predictive maintenance analyzes vibration, thermal, and historical failure data to intervene before breakdowns occur, reducing downtime and extending asset life. Beyond the factory floor, digital twins are emerging as a powerful enabler. Manufacturers can simulate new fiber designs, materials, or process changes virtually, reducing risk and accelerating innovation without disrupting live production. End-to-end traceability, powered by AI and data platforms, ensures every fiber reel is linked to process parameters, critical for compliance, certification, and high reliability deployments. AI is also reshaping operations holistically. Supply chain automation improves demand forecasting and production scheduling, while energy optimization algorithms reduce power consumption and carbon footprint, aligning manufacturing with sustainability goals. Importantly, this evolution doesn't remove people, it elevates them. Workforce roles are shifting toward data-driven supervision, AI governance, and process optimization, supported by focused reskilling. The result is a manufacturing ecosystem that is more resilient, more sustainable, and fundamentally more scalable, ready to support next-generation fiber architectures and extreme-density cable designs.
Given these advancements, what are the most cost-optimizing technologies expected to dominate soon?
The most cost-optimizing cable technologies are those that collapse deployment complexity while extracting maximum fiber value from every physical pathway. First, outdoor-indoor fire-rated cables with long-distance blowing capability are becoming foundational. They remove the need for separate indoor and outdoor inventories while meeting strict CPR and UL fire safety requirements. When paired with low-friction, microduct-optimized jackets, they enable longer blowing distances, fewer intermediate access points, faster installations, and materially lower labor and civil costs. HFCL's fire-rated microduct cable platforms are purpose-built for these mixed environment deployments. Second, compact outdoor drop and tonable cables are emerging as a cost lever in access and FTTX networks. Their reduced diameter, easy handling, and built-in traceability shorten installation cycles and significantly cut fault localization time in dense urban and campus builds. Third, in data centers and ISP backbones, UL-listed, CPR-compliant ultra-high-density cables are redefining cost efficiency. Scaling from 1,728 fibers to 3,456 fibers and now towards 6,912 fibers. These architectures allow massive capacity expansion inside existing trays and ducts, avoiding expensive pathway expansion and downtime. HFCL's high-density cable roadmap is aligned precisely with this need. Then there are microcables with ultra-compact, lightweight designs that simplify installation in congested ducts, aerial routes, and urban environments. They reduce pulling force, enable longer blowing distances, minimize civil work, and provide flexible, cost-effective deployment for FTTX, access networks, and dense fiber expansions. Supporting this shift are all dielectric designs that reduce material cost, direct burial and aerial cables that bypass duct construction, and long reach, low attenuation fibers that lower amplification and power requirements. In short, the winning technologies are not just cheaper cables. They are designs that deliver more fibers, safer installs, and faster scale within the same physical and regulatory constraints.
Great. Now, shifting our focus over to the heart of AI workloads, what are the biggest changes happening in data center interconnects?
Three things: hyperscale expansion, AI-driven workloads, and east-west traffic growth. Networks require high density, low loss, plug-and-play interconnects, especially MPO, MTP, and parallel optics.
This is a very critical area. How do MPO or MTP structured cabling systems support future AI or ML workloads?
They allow scalable 400G, 100G, 400G, and 800G deployments without rewiring. As AI clusters grow, MPO, base fanouts, and trunks enable quick rack scalability and uniform performance.
That speed and simplicity are exactly what operators need right now. What are the emerging trends in DCI cabling for 2025 and beyond?
800G and 1.6 terabits Ethernet nodes, co-packaged optics and silicon photonics, low loss, high count fiber backplanes, polarization maintaining fibers for coherent systems, and finally the push for modular plug-and-play ecosystems are some of the trends that are supposed to dominate the DCI cabling segment.
Excellent forward-looking indicators. Now, considering the environmental impact of scaling up so rapidly, how is the industry balancing sustainability with high-performance fiber designs?
We're moving to microcables, gel-free designs, lower diameter fibers, recyclable materials, and energy-efficient manufacturing. sustainability is no longer optional. Tender documents now demand quantified carbon reduction metrics.
To pull all these pieces together, what should telecom operators invest in today to stay future ready?
High-density fibers, bend-insensitive solutions, modular MPE infrastructure, and hybrid cables that support both data plus sensing. Future networks must be scalable from day one.
Sound advice for the market. On the human side of this transformation, what skills should engineers build for the fiber networks of the future?
Understanding photonics, fiber characterization, MPO testing, AI-driven network automation, and sustainability metrics are a few skills that engineers must know.
It's time for a rapid fire. Say the first thing that comes to mind. Most exciting future cable type?
Hollow core hybrid microcables.
One technology that will disappear?
Traditional loose tube designs for certain use cases.
One trend everyone is underestimating?
Fiber sensing in mainstream telecom.
One word for the future of fiber?
Limitless.
That is a perfect word to summarize it. To wrap up our technical discussion on a realistic note, what challenges remain for the adoption of advanced fiber technologies?
Adopting advanced fiber technologies faces several challenges. High manufacturing costs and complex fabrication processes make hollow core and multi-core fibers expensive compared to traditional glass fibers. Scaling production while maintaining ultra-low loss and consistent quality remains difficult. Interoperability issues and the absence of universal standards hinder seamless integration into existing networks. Deployment requires specialized splicing, testing, and handling, increasing installation complexity and cost. Finally, market readiness is limited as operators seek proven reliability and clear cost benefit before large-scale investment. Overcoming these hurdles will require innovation in manufacturing, standardization, and ecosystem collaboration.
Thank you so much, Jayuri, for these insights. And that brings us to the end of this chapter in the HFCL time machine. Until next time, stay connected to what's next.
You've been listening to HFCL Time Machine. For more conversations like this, find us on LinkedIn, Instagram, and YouTube.